Hi everyone, welcome to my YouTube channel again. And today is going to be the last summary before we start learning about the semiconductor fabrication. So today we're going to make a summarize about some short channel effects that occurs because we want to shorten the channel to make a smaller device like Samsung or TSMC are making the semiconductors. They want to shorten the device. So today we're going to learn about what happens if we shorten the channel. We're going to learn about what happens and some solutions, and making some solution. We call it a knob in this field. So to start with the capacitance of MOSFET. Before we start learning about the short channel effect, it is most important to learn about the capacitance of MOSFET. So I'm going to make a very short review about it. So let's have a look with this diagram. There are three states in the VGS. If we make the VGS lower than the flat band voltage, we call it is in the accumulation state. So if it is in the accumulation state, there are a lot of holes packed each other in the substrate. And of course, it is in the accumulation state, there is no channel. So as you can see here, because it is lower than the flat band voltage, which means it is lower than the threshold voltage, there is no channel, and there is only oxide capacitance located here. Let's look at the second state, which is between the flat band voltage and the threshold voltage. Also, because it is under the threshold voltage, there shouldn't be any channel, and the electrons are depleted in the substrate. So only source and drain junction capacitance junctions are here, and because it is in the depletion region, there must be depletion capacitance, and also there will be oxide capacitance located here. And now let's look at the final state, which is going to be in the inversion state, because the VGS is higher than the VTH. Because it is over the threshold voltage, there is a channel, and which makes the source and drain in the short status, looking in the electric circuit perspective. So there is going to be only oxide capacitance located here, because the depletion capacitance are getting short. Only oxide capacitance are here. Now we're going to look with the subthreshold swing. So what is subthreshold swing? We call it, when it's under the threshold voltage, we call it is in the subthreshold. As you can know from the wording subthreshold, it means it is under the threshold voltage. So we're going to define the swing under the threshold voltage. So as you can see here, we made an equation which is round Vg over round log ID. We call this a subthreshold swing. As you can see in the graph, log Vg over log round Vg over round log ID means the opposite of the slope, which means 1 over the slope. So if the slope is steeper, it means the SS subthreshold swing is very small. So a good device has a very low subthreshold swing. However, this subthreshold swing cannot be under 60 millivolts per decade. So these days we try to make any device, we're trying to make a good device. So we're trying to make a device which has subthreshold swing nearby 60 millivolts per decade. Some device can have very poor subthreshold swing, because if this device is a very poor device, it can occur like in this red line. under the threshold voltage, we call it subthreshold. In the subthreshold, there will be some leakage current, as you can see here. So this is a very bad device. So we are trying to make the swing value very low to make a good device. Now I'm going to introduce you with some short channel effects. Firstly, I'm going to talk about with the punch through. So what is a punch through? So punch through means when you shorten the channel, some depletion region in the drain and the depletion region in the body gets overlapped, making some leakage current. As you can see in the diagram, some of the depletion region in the drain and depletion region in the body and source gets overlapped, making a lot of electrons to flow and making some leakage current. We can know this by looking at the graph. As you can see here, under the threshold voltage, there are some leakage currents. So we can know, oh, this leakage current happened because of the punch through. We can also know with looking at the energy band diagram, when it is in the off state, of course, there shouldn't be any electrons because the conduction band and the Fermi level between the gap is very high. So the electrons are very hard to jump over the conduction band. So we're trying to make a device when it is in the off state. We're trying to make a device that has no leakage current. However, because of the punch through, when it is in the off state, even though it is in the off state, the Fermi level gets very near to the conduction band, making a lot of electrons to flow, making some leakage current. So there were some knobs about to solve the punch through effect. The first solution was to increase the substrate doping. So if we increase the doping, there will be less depletion region. So this is what people try to solve to solve this punch through effect, making the substrate higher doping. Making the substrate higher doping, it could solve the depletion problem. However, there were much more junction leakage such as BTB tunneling, and it made the mobility lower. So making the mobility lower, for example, if we want to put 10 voltage into the gate voltage, but only 8 voltage were received from the drain. So making this mobility lower made some problems that VG, the gate, couldn't control the device. So another solution were suggested by some people. They suggested the solution by making an SOI device. So SOI stands for silicon insulator. They put a silicon on an insulator to make the depletion region decrease. Then the problems occurred in the punch through. However, making silicon on the insulator, there were some self-heating problems, and of course we added some materials. From the perspective of the company, some costs were also problem. However, SOI device is a very good solution to reduce the depletion region and reducing the punch through. But these days, a lot of semiconductor companies are not using this SOI solution. By making the channel shorter, there were also problems with lowering the threshold voltage. Because the channel got shortened, as we put a bias to the drain, of course, because we put a voltage to the drain, the barrier got lower, and making the drain barrier lowering, the drain barrier also made the gate voltage barrier lowering, making a leakage current. So we also call this audible effect stands for drain-induced barrier lowering. As you can see from the naming, the drain barrier made the gate voltage barrier lower too, and made some leakage current. So as you can see from the TCAD simulation, this is the status when the channel were long, and this is the diagram for when the channel were short. When the channel were getting shorter, there were a lot of leakage current, as you can see from the diagram here. So this is just a basic diagram to make your understanding better. So when the channel get shorter, when we put a bias to the drain, the barrier got lower, making some leakage current here. Now there are some more short channel effects, which is channel length modulation, and also some gate induced drain leakage, which we call it a Guido effect, and also some MOSFET breakdown, and some source drain series resistance, which made some contact issues. However, these short channel effects are all same that I told you just previously. So now let's see what we use in the semiconductor field. We use a multi-gate transistor such as FinFET because these problems, short channel effects and a lot of problems happen because the gate voltage couldn't control another part such as body, drain or source. So these problems happen. So what people tried to make the solution was to put the channel vertically. They pull up the channel so the gate could control the three part of the channel. So if we can control the three part with the gate, they thought it is much easier to control the device. And of course, now like Samsung or TSMC or Apple or any other semiconductor companies, as you know, they also use multi-gate transistors such as FinFET. Nowadays, they also use MBC-FET or whatever they call, depending on what they name with the multi-gate channel. Any devices such as your smartphone or your iPad or your laptop, there is a lot of semiconductor structure consisting with the FinFET structure. So today it was a very short summary with the short channel effect, and in the next class I'm going to talk with the real fabrication of semiconductor. So thank you for visiting my YouTube channel, and I hope you enjoyed it. Thank you.